On September 1st of last year, a group of 16 researchers made a pivotal revelation that sent shockwaves through mainstream researchers. They distributed a paper specifying their discoveries, which tested our central understanding of the universe. Utilizing the powerful James Webb Space Telescope, these scientists observed distant universes and uncovered something genuinely startling. Until this revelation, the common thought in astronomy was that the universe went through a period of rapid expansion followed by a cooling phase. This cooling phase eventually led to the formation of the first stars and galaxies during what researchers refer to as the Dark Ages. However, the galaxies observed by the team appeared astoundingly developed, resembling our own Milky Way and showing a level of maturity far beyond what was expected. This discovery suggested that these ancient universes probably existed well before our own. This finding carries significant implications for our understanding of cosmic history. It challenges the traditional story of the universe's beginnings, especially the widely accepted idea of the Big Bang as the definitive starting point. While the Big Bang theory posits a single event that marked the beginning of our universe, the discovery of these ancient galaxies suggests a more complex timeline. Prior to the mid-19th century, the dominant view among scientists was that the universe was static and eternal, with no expansion or contraction occurring. This belief was overturned by the observation of astronomer Vesto Slipher, who saw certain nebulae showing rapid movement away from us, attributed to the movement of our own galaxy. Further observations, especially from the Lick Observatory in Arizona, contradicted this explanation. The crucial breakthrough in unraveling this mystery was made by Edwin Hubble, who demonstrated a clear correlation. The farther a nebula was from us, the faster it appeared to be moving away. This precise evidence aligned with the predictions of Albert Einstein's theory of general relativity, which suggested that spacetime could expand or contract. By tracing the universe's expansion backward through time using the equations of general relativity, scientists arrived at the concept of a singularity, a point of infinite density and temperature from which all matter and energy originated. This singularity is often associated with the event known as the Big Bang. However, this raises significant questions about what existed before the Big Bang, if anything was there at all. Was there truly nothing, no space, no time, or are there aspects of cosmic history that remain beyond our current understanding? To visualize this concept, consider the analogy of the surface of a balloon. Imagine our universe as the surface of the balloon expanding from a smaller size to its current dimensions. As the balloon expands, objects marked on its surface move farther apart, illustrating the concept of cosmic expansion. In this framework, the scale factor serves as a measure of the universe's size, similar to a ruler used to measure the balloon's dimensions. At present, our universe has a specific scale factor, but in the past it was smaller. As the universe expands, galaxies and other cosmic structures move away from each other, driven by the stretching of spacetime itself. In the future, the scale factor of the universe will continue to increase, reflecting the ongoing expansion of the universe. This perspective offers a glimpse into the vast and intricate complexity of cosmic history, inviting further exploration and investigation into the mysteries of the universe's origins. As you gradually let the air out of the balloon, everything on its surface begins to move closer together. Eventually, if you were to completely deflate the balloon, you'd be left with a small, flat piece of rubber. This is analogous to the concept of the singularity, a point in the universe's history when everything was incredibly close together, with the utmost intensity, hot, and extremely dense. If we extrapolate the laws of physics backward in time, we arrive at a moment approximately 13.8 billion years ago when the temperature and density of the universe became infinite. However, just as we begin to grapple with this concept, it becomes apparent that the situation may not be as straightforward as it seems. Current evidence suggests that we shouldn't necessarily apply Einstein's equations all the way back to a singularity. Observations indicate a critical moment just before 10 to the power of -32 seconds after the Big Bang, during which the universe underwent a rapid expansion known as cosmic inflation. This period of inflation provides crucial insights into the universe's expansion on a grand scale, explaining why the universe appears so uniform and shedding light on the formation of galaxies. Yet, even with the concept of inflation, the singularity remains a challenging concept. Its extreme density and temperature bring quantum forces into play, complicating our understanding. General relativity alone may not suffice to fully grasp the singularity's nature. This early period of rapid expansion helps resolve some of the puzzles within the Big Bang theory, but it also prompts a reevaluation of our understanding of cosmic expansion and the universe's beginnings. The exceptional nature of the singularity suggests that it might not represent the entire picture. Mathematical singularities often indicate gaps or limitations in a theory. In the case of the singularity, the clash between general relativity and quantum mechanics highlights the need for a broader understanding. Scientifically, we are still exploring the idea of whether there was truly a beginning to spacetime. Sir Roger Penrose has proposed a new framework, suggesting that events crucial to the formation of the universe, including the creation of galaxies and stars, may have occurred before the Big Bang itself. This challenges our conventional understanding and opens up new avenues of exploration. In this broader context, the universe's ultimate fate remains a subject of speculation. As we fast forward through time to eternity, envisioning a universe dominated by photons as black holes evaporate, we face the timeless nature of these particles. Photons, following null geodesics, move along paths where time and space essentially cease to exist for them. In a sense, they swiftly traverse the fabric of spacetime without experiencing the passage of time. Imagine turning on a flashlight for a brief moment and then turning it off. The instant the light dashes away from the flashlight marks event A, while the moment it reaches a specific point away from the flashlight represents event B. The spacetime separation between these two events is calculated using the equation ds(2 = 0. This means that the photon emitted from the flashlight moves from event A to event B, simultaneously crossing through both space and time in a manner that offsets any net change in the spacetime interval. This remarkable behavior of photons, where they lack a rest frame and do not have an individual clock, aligns with a key principle in physics: the constancy of the speed of light. No matter where you are or how you're moving, light always travels at a consistent speed. If photons had a fixed reference point, it would appear as though light is not moving from their perspective. This fact challenges our understanding of the speed of light and highlights the unique nature of photons. The equations governing light, known as Maxwell's equations, have an intriguing property. They are conformally invariant. This means that the equations remain unchanged regardless of whether you scale up or down the system. In essence, the vastness of the universe or the tiny size of quantum particles all appear the same when described by these equations. By applying this conformal picture to the concept of the Big Bang, we can envision a scenario where the universe's initial state extends beyond the traditional concept of the Big Bang singularity. This mathematical approach allows us to characterize the universes. By applying this conformal picture to the concept of the Big Bang, we can envision a scenario where the universe's initial state extends beyond the traditional concept of the Big Bang singularity. This mathematical approach allows us to characterize the universe's beginning in a way that extends back infinitely. Einstein's theory of relativity provides crucial insights into understanding when the universe began. According to Einstein, energy and mass are interrelated, and this relationship is further elucidated by Max Planck's equation relating energy and frequency. This interconnectedness between mass and frequency underscores the role of mass in defining the passage of time. As we consider the distant future of the universe, we envision a scenario where the universe becomes essentially empty, populated only by photons. In this distant future, the universe's state may resemble that of a new Big Bang phase, suggesting a cyclic nature to cosmic expansion. This concept, known as conformal cyclic cosmology, challenges conventional ideas about the universe's beginning and end. It suggests a continuous cycle of expansion and contraction, where each cycle mirrors the previous one. This cyclic model emphasizes the significance of the Hubble parameter, which measures the rate of the universe's expansion. As the universe expands and contracts in a perpetual cycle driven by the interaction of dark energy, it embodies a timeless and interconnected reality where past, present, and future intertwine. In our everyday lives, time flows continuously, shaping our experiences as a sequence of moments or snapshots. Each moment unfolds, leading to the next in a continuous cascade of events. If we were to envision all these moments lined up, every natural occurrence and every event in the vast expanse of the universe, it would capture the entirety of cosmic history, from the explosive birth of the Big Bang to the formation of stars in the Milky Way, from the emergence of life on Earth billions of years ago to significant events happening now. They all coalesce into our sense of now. Yet Einstein's theories of relativity present an intriguing twist to this seemingly straightforward concept of now. According to special relativity, an entity's perception of time can differ depending on its motion. This means that individuals moving at different speeds will experience time differently and may cut through the fabric of space-time at different angles, shaping their unique now slices. To illustrate this, imagine an entity in a distant galaxy billions of light-years away from Earth. As this entity moves away from Earth, its now slice crosses the region of space-time differently, causing its present moment to skip back in Earth's history. Conversely, if the entity moves toward Earth, its now slice tilts toward Earth's future, offering a glimpse of events yet to unfold. This concept becomes even more fascinating when applied to photons, particles of light. For photons, there is no distinct past, present, or future. Their now encompasses all of time simultaneously, just as we perceive all of space to exist. So too does all of time envelop every event that has happened or will happen. This idea echoes Einstein's famous "when we combine quantum physics with gravity and introduce the concept of inflation, we arrive at the idea of eternal inflation, a scenario where most of space is endlessly expanding, punctuated by pockets where inflation stops. Within this,